Here's the beginning of section 5.4, where we look at motion and velocity dependent resistive forces. We want to understand the two models for velocity dependent resistive forces and when to actually apply each model. And we also want to be able to begin looking at some of the equations so that we can do some problem solving with these resistive forces. Now, we've already talked about friction as an object moves across a surface and that type of resistive force. But what about moving through a medium? Resistive forces, or a capital R, when you're moving through a medium, is really that force that exists when an object is trying to move through some type of fluid or medium. So try to think of some examples. Maybe this is a person trying to walk through waist-deep water. Maybe this is your hand sitting out the car window while it's kind of going up and down in that wave pattern, and you're feeling that resistive force of the wind blowing on your hand. Maybe it's someone skydiving, or maybe it's dropping a pebble into a glass of oil or honey. Each of these different examples would have an object moving through some type of medium where that medium would exert a resistive force. Now, the magnitude of that resistive force depends on the relative speed between the object and the medium. Think back to the example of like a person running through water. If you think about your motion through that water, if you were in waist-deep water and were simply walking, you wouldn't feel that much of a resistive force moving against you. But when you try to all-out sprint through waist-deep water, you definitely recognize that that force against you seems to be getting stronger and stronger the faster you try to move. That's what we mean when we say that these resistive forces are dependent upon the speed of the object through that medium. The direction of the resistive force is always opposite the object's motion. So whichever way this thing is moving relative to the medium, the resistive force is going to work in the opposite direction, much like friction would do. Generally, when R goes up, it's due to that velocity going up as well. The faster you try to move through the medium, the more that medium is going to resist that object's motion. Oftentimes, this can be a very complex relationship, but we can simplify it into two fairly simple models. One of those models has that resistive force proportional to velocity, just plain V. This is for objects that are moving through a liquid at a lower velocity or very small particles like dust in air. The other model has the resistive force proportional to V squared. These would be for larger objects and things that might be in free fall, more like a skydiver. So let's look at Model 1 in this screencast, where the resistive force is proportional to velocity. The use for this model is for objects that are moving through a viscous medium at relatively low speeds. So we're talking about thicker medium, like honey or maybe water, and we're talking about things that are moving at relatively low speeds. If this is the case, we have the equation R equals negative BV, where V is the velocity relative to the medium, and B is a constant that depends on the properties of the medium, the shape of the object moving through it, and the dimensions of the object. If something was more streamlined and aerodynamic, B would be a lower value. If the medium itself was more fluid and allowed things to move through it easier, like water, then B would be a lower value. If you're talking about something that's very irregularly shaped or maybe hairy and it's trying to move through honey, that would be a much higher value of B. The negative sign here means that the force works against the direction of your velocity. So whatever the direction of V is, the resistive force will be opposite that. So let's kind of think about an example here. Let's say that you have maybe just a big glass of water, for example. And we allow this mass M to be released in the water. Now, if we look at this object that's kind of sitting in the water here, it's going to be falling down through that glass of water. As we look at that mass, we obviously know that gravity is going to be pulling down on that mass. And again, we know that there's going to be some sort of resistive force, where that resistive force should be equal to negative BV. Summing up the forces acting on this object as it's just falling through this glass of water, we will be summing up forces in the y direction, and those forces would be mass times gravity, or the gravitational pull on the object, minus the resistive force, where that resistive force would be that negative BV. And we could then set that equal to MA. What you see in my equation here is that we've done just that. We took mg minus bv as the two forces that would be acting on this object as it falls through the medium, and we set it equal to ma. But instead of writing a, we instead wrote the a as a dv dt. So again, we're thinking of this in terms of calculus, and that acceleration is really a change in velocity over time. In the next piece of the equation here, what you see is that I've just divided everything by an m. When I divide this side by an m, those m's cancel out. When I divide this side by an m, those m's cancel out, and we'll need to keep an m on the bottom underneath that b that's being multiplied by the v. We're going to talk about this equation in the next slide. That particular equation is what we call a differential equation. It includes both the value v and the derivative of v. So if we were to write that one more time on this slide here, the equation looked like this. dv dt equals g minus b over m times v. So that's what we mean by differential equation. It's an equation that has a variable, and it also has the derivative of that exact same variable in the same equation. Solving differential equations can be very tricky, but initial conditions can help. Remember, we said that this object was dropped from rest, which means that the initial velocity is equal to 0 when time is equal to 0. We'll practice solving some differential equations in class another time. For now, we'll just look at this simplified version. So we know that the object is accelerating due to gravity. So what happens to the velocity as time goes on? Again, imagine your glass here, and that object being pulled on by gravity. It started out with a very small resistive force because it started out moving very slowly. In fact, at 0, when the velocity was 0, the resistive force would also be 0, since the resistive force is dependent upon that velocity of the object. Now, as the object continues to fall, it would be getting faster and faster and faster, which means that if we looked at another time t into this motion, the resistive force up here is going to start changing size. It's going to start getting bigger, because as this velocity increases, the resistive force is also going to increase. Bigger velocity means bigger resistive force. So now this force is a little bit bigger, and the object is now going to have a different acceleration. That acceleration due to gravity that used to be 9.8 is now something less than that, because we have more of this resistive force working against it. As time goes on and it continues to fall, this resistive force is going to get even bigger, because again, increasing velocity is going to result in an increasing resistive force. At some point, these two forces, the resistive force and the gravitational force, will eventually become equal to each other. And that's exactly what this diagram here is showing you. The body starts out at rest. It starts to fall where the drag force is now increasing and becoming larger. And eventually, the drag force is going to be equal to mg, or that gravitational force pulling straight down. At that point in time, the object is no longer accelerating, because as we look at this free body diagram, we can see that this object has reached equilibrium. Each force is equal on either side of the object. So equilibrium has been reached, there is no more acceleration, and without any acceleration, the velocity is now going to be constant. If the velocity is constant, the resistive force is also going to be constant. So the drag force is not getting any bigger at this point, it's just staying the same. And the velocity of this object is also not getting any bigger. That's when we have finally reached what we call terminal velocity. When the acceleration equals 0 and all forces are balanced, that velocity will be constant, and this terminal velocity will now be the maximum velocity that an object can possibly fall with due to those resistive forces. So essentially, we get this equation in terms of the forces acting. mg going one way, bv going the opposite way, where that v is now a terminal velocity, since we say that these two forces are now equal to 0. They've balanced each other out, which means that we can actually solve for an expression for terminal velocity. Terminal velocity is now equal to mg divided by that coefficient b. Again, this holds true for model number 1, where we have these objects falling through a relatively viscous medium at relatively slow speeds. Now, let's go back to that differential equation. Remember this thing? If you solve this differential equation, which I'm not going to show you how you solve that just yet, I will show you one means of solving differential equations later on in the class, but if you were to solve this, you would find that the solution to this differential equation in solving for the velocity v at any time t is equal to this expression that we have here, mg over b multiplied by the quantity 1 minus e to the negative bt over m. If we rewrite this, we would recognize the fact that mg over b is exactly what we said terminal velocity was equal to in the last slide. So we can simply replace that with v sub t and keep then the expression in the parentheses of 1 minus e to the negative t over tau. Now let's talk about tau for just a second. Tau is just another way of writing this b over m that we had here. So tau is actually equal to m over b. And you'll see that the expressions are equal if that is the case. We can put in a tau or we can put in this negative b over m. Looking at this equation, we see that terminal velocity is not actually ever reached. In fact, if we were to draw a graph of terminal velocity, or this velocity function that we have here, if we were to actually graph this function, you can look at the graph on page 141 in your books, or you can take a look at my quick sketch that I'm going to create here. If we created a graph of the velocity of the object at any time t, and we actually graphed this function, what we'd find is that this function looks something like this, where terminal velocity is now becoming a bit of an asymptote for this thing. This value here would be considered v sub t. And the graph of this approaches that value, but it never actually reaches it, which means that terminal velocity is never actually reached. For all practical purposes, we could approximate it as reaching a constant value at some point, sort of where the graph levels out, but it never actually hits that value of v sub t. The problem with that is that we can't actually compare time intervals to get there. So if we had a skydiver falling through air, or we had maybe a rock falling through honey versus maybe a penny falling through honey or a penny falling through water, we can't say, hey, it took the rock this long to reach that terminal velocity, but it only took the penny this long to reach that terminal velocity. There is no time that it ever actually reaches terminal velocity, since this graph actually never touches that asymptote. Here's where we've come up with this constant tau. So that's where we stuck that in the equation here. Why we defined that as that m over b. The time constant tau is a way for us to look at the time interval required to reach only 63.2% of the terminal velocity. So instead of looking at this graph and saying, you know what, the graph never actually reaches this value, we could say, let's take 63.2% of that value and talk about maybe this spot here. The graph does in fact reach that particular location, and now we could look at what time, or tau, what time is required to get there. The reason why we choose 63.2% of the terminal speed, I know it sounds kind of crazy, why 63.2% of the speed? It does come from the math. Basically, we're looking at the time interval t, where t is actually equal to tau. So essentially, when we come back up to this exponent on the e here, if t and tau were the exact same thing, then the exponent on the e would actually be equal to 1, which you see down here. So if we actually take 1 minus e to the negative 1, we actually get 0.632, or 63% of the actual terminal velocity. This is now a way that we can compare different objects in how long it takes them to reach that terminal velocity by looking at the time constant tau.